Hello everyone, this is David with MLC CAD Systems. Today we're going to discuss the SOLIDWORKS plastic simulation. So if you're not familiar with plastic simulation, that's perfectly okay. I'm going to give us a full plastics overview, discuss kind of what it is, a little bit of the capabilities. And we'll jump in some examples so we can take a look at this in action. We'll start with a basic plastics analysis. We'll move on a little bit more advanced and jump into a packing and cooling time analysis, and then discuss some additional capabilities. So plastic simulation, like some of the other simulation capabilities from SOLIDWORKS, is simply an add-in built into our CAD package. So that means we don't have to import or export any files to another application. It's built right into our design software. In addition to analyzing our design of molded products, plastic simulation also lets us evaluate the injection molding process itself, making sure that we're not wasting time on the cycle time for individual parts, driving up cost, and we're not wasting any time on rework of any tooling or molds or having to potentially scrap molds, which can be extremely costly. The way that it's broken down is into three different flavors. There's plastic standard, professional, or premium. The way I like to think of it is plastic standard is really geared toward the filling stage in your process, whereas professional is the packing and cooling phase. And then with premium, we have some post-processing results with respect to warping and detailed sink mark analyses. So let's take a look. I wanted to first start off by discussing an overall plastic basic analysis. With that, we can discuss the different element types, meshing parameters, and give an overall layout of the plastics user interface. We'll then go over some pre-processing options, run a plastics analysis, and discuss the types of results and information that we can get out of this. Let's dive in and take a look. Alrighty, I've got a file that we can take a look at here. Let me go ahead and get that open. And as I was mentioning, plastics is just one of our add-ins. So from my add-ins tab, I can turn it on here. Or another way to access the add-ins is to go to the drop-down arrow to the right of your system options gear symbol. Go to add-ins, and that will allow you to turn it on either for just this session or every time you launch the software. Plastics is down here towards the bottom, by the way. So now that we've got plastics turned on, let's go ahead and start our analysis. Whenever we say we have a new study, there's a couple of things that we want to define here. First would be the study name, and then next we have the injection process. Now, the example for this basic analysis will be a single injection material, though plastics can also do analysis for bi-injection, co-injection, gas assist, water assisted, or multiple material overmolding. So we would set that at the beginning so it knows what type of injection process we're going to follow. And then we pick the type of elements. We actually do this at the beginning. Now I'll discuss the mesh in more detail in a few moments. But all we need to do here is determine whether we want to use a solid or a shell mesh. Now, for a single material, we can use a shell mesh, but anything other than that, so bi-injection, co-injection on down, those all have to be solved with the solid. So shell will not be available unless you're doing a single material injection process. So just be mindful of that. That's what we'll select for this one. I'll go ahead and hit green check. And here we have our plastics tree. So as you can see, I've got my injection units where I can specify some of the flow parameters as well as the material. This second tab here is just showing the solid bodies that we have in the file. And by default, this will come up as your cavity, right? If I had more than one solid body, I would need to designate which ones are the cavities. You could also have the actual mold in here as well, and you would right click and tell it that it is the mold rather than the cavity. I'll get into boundary conditions in just a few minutes. Let's go ahead and just like regular simulation or flow simulation, let's start filling out the analysis details from the top of our simulation tree to the bottom. So I'm going to right click on my injection units here and go to settings. So before I can fill out any of this data, which I'll discuss in a minute, I need to first pick the material. So I'm going to go ahead and grab the material from the material database. And I wanted to let you know you can sort by company in these materials or sort by family. That's going to be really helpful when you get into your own analyses, because there are thousands and thousands of materials in here. Of course, if you can't find this crazy specific or maybe custom material that your company's got, you can always create your own or copy one of the materials from here that's similar and modify as needed to fit what you've got. So what I'm going to bring in here is this BASF Novolin 1100H, pretty common injection material. I'm not going to review the material properties for now, but you can see anything that you would want to dictate that would affect the analysis could be done so here. We'll go ahead and click OK. And now that we've got a material that we're going to be injecting with, all of these boxes sort of wake up or become active now that we know what we're using here. First, we can see the melt temperature. This comes from the material. Now, I'm going to leave it on the default. I'm not going to change into some kind of custom melt temperature. We also get a default mold wall temperature. This can be changed as well if it's, of course, heated or if it's something other than like an ambient room temperature. Then we have some fill properties, right? You can manually define more than this, but most analyses, all we need to use is this automatic. We have the injection pressure limit of the machine, and then the point at which we want it to switch from the flow stage or filling stage to the packing stage of the process, right? If we have a specific temperature criteria for short shots, we can enter that here. But as I said, for the most part, these default properties will get you what you need. We're not going to discuss it for now, but you can also have some more parameters and information about the mold wall temperatures and heat transfer coefficients. In the next analysis that we'll show later, we'll also discuss some of the packing input parameters. For our filling analysis, I'm going to click OK. So now that I've got that, I want to go ahead and add my injection location, which is done with our boundary conditions. And just like regular static FEA, most of these commands that I'm going to access from my simulation tree is accessed via a right click. So if you right click, you'll probably find the button you're looking for. We can add control valves, a different mold wall temp here, a specific clamp force direction, or change the clamp force tonnage, or we can add some coolant parameters. I'm going to go ahead and add my injection location. And for that, I've just got a point, a sketch point, on the surface that we're going to be injecting from. So this is mimicking the gate or the location where the molten plastic is entering the cavity. So that's where it's filling from. Now, if we were doing a solid mesh, we could also use more specific information. If we had something other than this pointer diameter that I'm using to represent the gate right now, we could actually model our physical gate geometry being a rectangle or whatever kind of shape that you've got, and then say that that is our injection location, and it'll take that into account. Again, for this basic analysis, we're going to kind of walk through this thing pretty simple. Go ahead and hit the green check, and now that it's got the injection location, the material, we're ready to go ahead and mesh this. And we had chosen to do a shell mesh, if you recall from the input, that again is only allowed for a single injection material. The other thing that the shell mesh is intended for is a quick iteration to see if this thing is possible to be molded, get a quick idea of where your weld lines are going to be, as well as a basic fill time. Now for full accurate results, I always suggest running this with a solid mesh, but the shell mesh is a great advantage to run as a quick iterative pass, kind of check and make sure that all my inputs are correct before I do my full final analysis. I'm going to first go ahead and mesh this a couple different times. I'm going to mesh this really coarse, and I'm leaving this on uniform. Let's go ahead and hit the green check. So with this, you'll see that my mesh element size is not quite small enough to really represent what's going on here. I've got some tessellation around the corners of this, and it's not necessarily representing exactly what I want. This is a little bit blockier than I would want the part to end up. So let's come back and take another look at this. This time I'll go right click again and say create mesh and use a curvature base. And we'll also give it a little bit finer mesh. So I'm going to put it towards the middle and green check it. Now, just like with other simulation packages, we can create mesh controls for localized areas where our mesh is finer or more dense than others, so that we don't have to mesh the entire part with a very, very small size that would take longer to run. Now, from there, all we have to do is right click on our flow and choose to run. It'll bring up the solver window telling us how much of the volume has been filled as it's going. You'll notice on the results over there, or when we choose to flow or choose to run, we've got a couple of different options. We can run the flow plus pack, or run a flow plus pack plus warp and cooling. So the difference between those is coming back to those flavors of your licensing package for plastics. So flow analysis is what's available for the plastic standard. Flow plus pack is available in plastics professional, and the flow, pack, warp, and cooling is in our premium package. So with our standard package, we can get some really good insight as to what the cosmetics with respect to maybe potential weld lines or sink marks would be in this. Of course, we'll get an idea of the cycle time and just the overall ease of fill. There's a few other things that we could take a look at. We could look at the shear stress at the end of the fill, volumetric shrinkage, but with our fill analysis, as a designer, even if you're not manufacturing these parts or injection molding them in-house, this can save you a lot of time and money just by running through this before sending it off to whoever's going to make your tooling. So you can see I've almost filled here. I'm about 80%, and the plastic simulation will actually give us an animation as it's filling, so you can look at the fill or flow profile as it's filling the cavity. Alrighty, we can see I've got a max injection pressure, and I'll discuss that here in a minute. The main plot that we're looking at now is our fill time, right? So a couple of things that I would like to do here first is just check, like I would in the deformation, just look and see how it's filling the cavity. Would this be what I would expect? Does this make sense? We can also turn on and check for air traps. I'm going to just select my checkbox here, and you can look at these weld lines. Now the weld lines are where, of course, the flow front meets at 2 or more points, generally around holes. So that's why we're seeing when the flow wraps around this side and then comes around this side of the hole, they meet there, and that's where we get these weld lines, right? Which is what we're seeing with our plot. You can animate that again once we turn our weld lines off. Some of the other things that I would be interested in as a designer here would be simply the ease of fill. What I use this one for is, of course, just look for any features that may be a lot more difficult. Maybe there's another way, or there's something that's not critical to design that I could kind of reduce my injection molding cost as well as the fill time. You'll also notice that I have what's called this results advisor over here. So this is just telling me, yep, based on ease of fill, this is easy, it's not difficult or impossible to mold. It also tells me the injection pressure at the end of fill and that it's 66% of the injection pressure that I have available with the machine. And again, that was done under my input parameters using those defaults. I could also check for sink marks here. So turning that on, I'm looking at, of course, sink marks. This is looking at the location and a plot. Now, the actual geometry and deformation of true sink marks we can also obtain, but that requires the Plastics Premium licensing to get there. So we can also look at the temperature at the end of fill, so that way we can see, of course, we haven't done our packing phase or the cooling phase, but get an idea of how hot this thing is once it gets to 100% before we start the packing process. We can get an idea of the cooling time. And as I said, there's several other parameters, and I won't discuss them all in detail. We can look at shear stress, which of course affects the cosmetics. If we have too high of an injection pressure, that'll cause, or too short of a fill time, that'll cause, excess shear stresses in the port. But for the most part, that's all that we would want to look at for here. We've got a good part that's easy to fill. I've got my fill time on there. Doesn't look like, as far as the actual design, there's too much that we would need to change. Now, before we switch over to our other one, let's take a quick recap. For our first analysis, we were able to predict the fill time, ease of mold, take a look at air traps, some gate blush. We could have detected short shots as well, and actually that results advisor would have came up and told us that we had a short shot. We can use this to, of course, reduce our cycle time, reduce weld lines in areas that we don't want them cosmetically on the part, use it to prevent the dieseling effect, also minimize sink marks, and prevent any unnecessary rework for tooling. So for the next analysis, instead of looking at the fill stage, I want to take a look at determining the proper packing and cooling times. We'll go over the fill to back transition and the pack to cool transition. And ultimately what we're looking for is the cooling at the time that we can eject this thing from the mold, which is our true cycle time. So that cycle time is not just, the filling, it's the amount of time it takes to pack that, as well as for it to cool and eject from the mold. So let's go ahead and jump back in and take a look at this other file that I got. For this one, I created a second configuration. One of them was already solved. That's the exact same setup as the one I'm showing you now, just so we don't have to sit and wait for it to calculate. So if I come into this plastic study that's already started, just like before, we see our same tree. What I want to do is come in here to my injection settings. Just like before, we have all of our fill parameters. Notice down here that our switch point here is at 100% filled. Normally that's at like 99%, and then you would switch over to the packing phase. Once the cavity is filled, it'll start to cool and shrink, which is why we need to continue injecting and packing material in there, so after it shrinks, we reduce the amount of volumetric shrinkage in our part, and we don't have as much deformity. Click on this second tab here. That will bring up our pack settings. And instead of using the default parameters, I want to deselect this. So what I'm going to do is deselect my pressure holding time and change this to something much higher. I'm going to change that to 40 seconds. And the reason being is I want to determine the exact point that this thing gets to 100% fill and that it's not changing the mass, so that I know that that's my accurate packing time, right? So once it fills, we'll get the true packing time, and then, of course, the cooling results. Let me go ahead and green check that. So that's the only difference in this setup versus the one I'm going to show you that has results here in a minute. A little bit about how plastics works with respect to multiple studies. We can duplicate studies. Here we can copy, and we also have a batch manager, so we can come up with different scenarios, different geometries, and run them all at once. or we can use duplicate, modify parameters, and then take a look at different setup scenarios that way. This larger gate is the one that I had started my initial setup from. So let's go ahead and take a look at here. So remember, all I did here was just increase that packing time. So I should be packing it much longer than I need to. Let's take a look at what we've got. So under my results, I've got my flow results and my pack results. Before we jump into the pack analysis or the pack results, I want to look at the XY plot. So I'm going to say right click and read my XY plot. Let me move this so I can see a little bit better. And what I want to look at here is not my pressure. I want to look at the part mass. So I'm going to change my graph to show me the part mass. And what we're seeing is a really steady, almost linear input here under our filling stage, and then we switch over the pack stage, right? So if we look at between about, say, 16, 17 and a half seconds on, the mass of our part is not changing. So what that tells me from that graph is that I don't need to hold my pressure in the packing phase really much longer than this. So for the fill and pack, it looks like I could be around 20 seconds or so. Of course, that isn't cooling, but this tells us the fill and packing time in our cycle. Go ahead and get out of that. Let's take a look at the other pack results that we have. So I'm going to right click on my pack results and say read pack. One of the things I can do, you'll notice that this setup, they actually have the sprue and the runner involved as well. I'm going to deselect my runner visibility so we're just looking at the part. First thing I'll look at is just the volumetric shrinkage. It looks like overall in my part minimum is about 2%. And right around this gate area, we can see that it's a little bit higher, maybe 5% or so. Now, of course, I need to look at the temperature or at the end. So we can say, here's the temperature at the end of packing, right? I also want to take a look at the temperature at the post filling end. So that's the temperature at the end of pack, right? Now, for this material, the ejection temperature is 225. So I'm looking at my plot, my temperature plot at the end of packing to see how much of that part is at my ejection temperature. There's a couple of different things that I can use to manipulate and see the through thickness plots or graphs for. I've got clipping planes, so I can take a look at this, add in a clipping plane, and look at a section view of these results. Let's say maybe the right view. So this would show us the temperature right through the gate through this part, right? Can also use ISO clipping. So if I turn on the ISO clipping, set my minimum value here to what my ejection temperature is, then I can just validate and make sure that every part of the part, or area of the part, I should say, is below that ejection temperature. So what we've done here is just change from our defaults to evaluate a true packing time. Of course, we could come back, modify the input parameter, change it from 40 seconds to what we found from these XY plots under part mass to 20 seconds and just validate what we had found in our charts. But this is needed to get a full accurate cycle time, right? So in addition to the accurate cycle time, we're also, of course, as we just did, validating that we've gotten to our ejection temperature. This is going to aid in getting more accurate results for shrinkage. We can also change and switch solvers to look at the jetting effect. Where we would want to take this next would be could we use this in a family or multi-cavity mold to, now that we know the cycle time, how can we get the most amount of parts for that cycle time, right? We could do a family or multiple cavity mold. We could also look at the cooling system. Maybe adding cooling to this could help it reach the ejection temperature quicker. We can also use SOLIDWORKS plastics to help design or evaluate hot runners. We'd also include the mold wall temperature, evaluate any baffles or bubblers that we have in this. And of course, some post-processing will also look at warpage. How much would this thing potentially warp? And with our plastics premium package, in addition to warpage, we can also get accurate deformation for sink marks. So I hope with the couple of studies that we've ran through the day, I've given you a good idea of what it looks like to set up and run plastics analysis, kind of the different breakdown in our plastics packages. And this is a really great tool, for designers to make sure, of course, that they're not making a part that is going to be difficult to mold, causing up tooling, or they're not going to have to come back and redesign later after their mold manufacturer finds an issue in the molding stage. We can also predict costs by getting accurate cycle times, predict cosmetic information for warping and sink marks. We can even look at bifringement plots for transparent materials, do reaction materials and rubbers. And if you do plastic or molded designs, this is going to be a valuable tool to help make sure that your engineering department design team is running as efficiently as possible and coordinating with your mold manufacturer.